Okay, so this is a continuation of our discussion on chapter 3, the derivatives. And here we will be talking about higher order derivatives. In the previous discussions or sections, we only take the first derivative of the functions. And in this lecture, we will be talking about higher order derivatives, not just the first order. So usually in the first order derivative, we denote that derivative as dy dx. In This is in Leibniz notation, or this is equivalent in prime notation. This is also y prime. It's equivalent to dy dx. Or in d notation, we write this in this way, xy. This is in d notation. Now, if we want to determine the more higher order derivatives, or the next one, this is the first order derivative. Now, if we want to take the second order, then what we do is we take again the derivative of that first order. So we take the derivative with respect to x again of the first order dy dx. And this is equivalent to the second derivative, d squared y dx squared. So this is the notation for the second derivative in Leibniz notation. In prime notation, we use y double prime. In d notation, we just put here square, dx square. So the derivative of y, or second derivative of y with respect to x, that's the second order. If we want to go further for the higher order, if we want to the third order derivative, then we just take again the derivative with respect to x of the second order. And the result will be the third order, or this is d cube y dx cube. It's the third order derivative of y with respect to x. In prime notation, this is y triple prime. In d notation, this is dx cube y, third order derivative. And so on for the fourth order. Then it's the derivative of the third order. It's equivalent to d to the fourth by dx to the fourth. It's the fourth order. For the prime notation, we write here 4. Then you put it a quantity. There's a quantity in the exponent to denote that it's not y raised to 4, but it's the fourth order derivative of y. For the d notation, then you just make it cube f to the fourth. And so on until any nth order derivative in general. So this will be d raised to n dx raised to n. Y n, then so this is the different notations used in derivative. We can use any of them at the same time. So don't be confused. We can use the Leibniz notation or the prime notation, or this one, the d notation. The d notation sometimes mainly used in later on in differential equations. So how do we take the higher order derivatives? Let's take an example. A simple example. So if we have here, if y is equal to 3x squared plus 2x plus 1, determine the second order derivative, determine y double prime, or d squared y dx squared, or dx squared y, second order derivative. And in order to take the second order derivative, first we need to solve for the first order. So y prime, or dy dx, now will be equal to, this is our y. So the first term, we use the power rule. So we bring down the exponent, we multiply it with the coefficient, and the coefficient is 3. So it's 3 times 2, so this should be 6x, then raised to n minus 1 or 2 minus 1. 2 minus 1 is just 1. It's just raised to 1. Then plus here, so this is a linear equation or linear function 2x. So it's just equal to 2. It's the coefficient. It's just equal to the coefficient. And the derivative of 1 is a constant. It's equal to 0. So this will be y prime. Now, if you want to determine the second order, then you take again the derivative of the first order. So what's the derivative of 6x? It's just 6. It's just 6. And the derivative of 2 is just 0. So therefore, this will be our final answer. So the second order derivative of y equals 3x squared plus 2x plus 1 is just equal to 6. So that's how we determine higher order derivatives. Let's take more example. How about this one? If y is equal to 1 over x cubed. Determine the third order derivative. Determine y 1, 2, 3 at x equals 2. So this is a specific values. We need to determine y triple prime at x equals 2. And again, so we take we take the first order, second order, then the third order. So y prime. Before we take the derivative, we simplify this into a power rule so that we can use the power rule. We make it x raised to negative 3. We put x raised to 3 at the numerator, but we change the sign of the exponent. So it's x raised to negative 3. And we can now apply the power rule here. So y prime, first order derivative, so bring down the exponent, multiply it with the coefficient 1, copy, then we subtract 1. Negative 3 minus 1. So negative 3 minus 1 is negative 4. So this should be raised to negative 4. So that's y prime. Then we take the derivative again, y double prime. So it will be negative 4 times negative 3. And that will be positive 12. Then x raised to negative 4 minus 1. Negative 4 minus 1 is negative 5. And that is the second order derivative. And for the third order, y triple prime, this will be equal to negative 5 times 12. So it should be negative 5 times 12. And that is equal to negative 60. And x raised to negative 5 minus 1, or that's negative 6. But we want to determine the value of this at x equals 2. So we need the third derivative of y with respect to x at x equals 2. So this will be negative 60 times 2 raised to negative 6. So the answer will be negative 15 over 6. So this will be negative 15 over 16. So this will be our final answer. So this is the third derivative at x equals 2. Next. Next example. Determine the second derivative. Determine the second order derivative. Second order derivative. Derivative with respect to x of y equals the square root of x squared plus 2. So this is square root. It's a radical function. So before we take the first derivative or second derivative, we rewrite this one into exponential form. So x squared plus 2 raised to 1 half. And we can apply the chain rule and the general power rule. Our f of x will be x squared plus 2. Then we need to multiply the derivative of that function, x squared plus 2, which is equal to x. So we do that y prime. So apply our rule, it's 1 half. Y 1 half, bring down the exponent. Then copy. Then we subtract 1 to the exponent. The original exponent is 1 half. Minus 1 is negative 1 half. That's the general power rule. Now, if we apply the chain rule, we need still to multiply this one with the derivative of the function inside this quantity here. And the derivative of that, x squared plus 2, is just equal to 2x. Then if we simplify this, then y prime will be equal to, so we can cancel out 2 here, will be equal to x. Then I will bring down that negative exponent to make it positive. And it's 1 half, so it should be square root. So that's the square root of x squared plus 2. So this will be the first order derivative, y prime. But we want the second order, so we apply again the derivative. So this is a quotient, so we can apply the quotient rule here. So y double prime will be, according to quotient rule, log d high minus high d low over log squared. So log, our law or the denominator function at the denominator is x squared plus 2 square. This is the law. You multiply it with the derivative of the high, d high, or the derivative of the numerator. And the derivative of x is equal to 1. Then we subtract law d high minus law d high minus high d low. High d low, high is x, and we multiply it with derivative of the lower function, that's square root of x squared plus 2. And to take the derivative of that, actually we already did that. This is equal to y prime. This is just equal to y prime. It's the same as y prime, and it's x over the square root of x squared plus 2. Then all over low squared. So if we square the square root, then it will cancel out. This is equal to x squared plus 2. So this is the second order derivative. Now if we can simplify this one, so y double prime will be equal to here. So we have the square root of x squared plus 2 minus, here we make it x squared, square root of x squared plus 2 all over x squared plus 2. And we can add the numerator. The LCD will be x squared, square root of x squared plus 2. Then we multiply it with, cross multiply with the square root of x squared plus 2. So the square root will also cancel out. So it's just equal to x squared plus 2. Then minus, here, minus x squared all over x squared plus 2. Then here we can cancel out x squared. X squared minus x squared is 0. Then we simplify further, and this will be equal to, so y double prime, so what will be the remaining? 2 over the square root of x squared plus 2. So if this is over 1, we can multiply this, and we can multiply this. And this will be equal to y double prime. So 1 times 2, so it's just 2 all over x squared plus 2 times x squared of x squared plus 2. Remember, square root is raised to 1 half. if we multiply it with x squared plus 2, so what's the exponent of this one? It's just raised to 1. So they have the same base. In algebra, if we multiply to the same base term, then you just add the exponent. So here, it will be x squared plus 2 raised to 1 half plus 1. And 1 half plus 1 is just equal to 3 halves. So this will be x squared plus 2 raised to 3 over 2. And this is now our answer for y double prime. The second order derivative of y equals the square root of x squared plus 2. Another more difficult example. Let's try this. Given y equals 2x plus 1 cubed and multiply it with x minus 2, determine all the derivatives from the first order to the fifth order. So we need to determine all of them. Solution. So this is a product. Y equals 2x plus 1 cubed times x minus 2. We can actually expand this to x plus 1 cubed, but I can just apply the product rule directly to solve for y prime, or the first order derivative. So applying the product rule, so take the first term, copy, then multiply it with the derivative of the other. Derivative of x minus 2 is this equal to 1. Then you add this one with, you copy the second term, then you multiply it with the derivative of the first term. So the derivative of that, we bring down the exponent 3, copy to x plus 1, then you subtract the exponent with 1. 3 minus 1 is 2, so squared. And applying chain rule, so we need still to multiply this one with the derivative of this one. Derivative of 2x plus 1 is just 2, so we multiply it with 2. That's chain rule, and that will be our first order derivative. So before we take the second order, we simplify this one first. So we have 2x plus 1 cubed plus, we have 2 times 3, so it should be equal to 6. X minus 2 times 2x plus 1 squared. This is the first order derivative. Then we can now take the second order. So y double prime will be equal to the derivative of the x plus 1 cubed. So using chain rule, so bring down the exponent, copy to x plus 1, then 3 minus 1 is 2. Then you need to multiply it again with 2. Using chain rule, the derivative of 2x plus 1 is 2. Then here, it's again a product rule. So you can factor out that coefficient, or you can actually distribute it with x minus 2. It's the same. You just need to factor it out. Then copy x minus 2. Then you multiply it with the derivative of the second term. So 2 times 2x plus 1. Then it's not yet done. You still need to multiply it with the derivative of 2x plus 1, which is 2. Then plus, copy the second term, 2x plus 1 squared, and multiply it with the derivative of the first term, which is just equal to 1. Derivative of x minus 2 is 1. Then simplify for the y double prime. So this will be 3 times 2, 6, 2x plus 1 squared, plus here we can distribute now the 6. 6 times 2 times 2. So that will be equal to 4 times 6. That's 24. X minus 2 times 2x plus 1. Then plus 6 times this 1, 2x plus 1 here, times 6. So 6 times 2x plus 1 squared. And this will be y double prime. This is y prime. Then next, for the third order derivative, y triple prime. This will be, again, here will be 2 times 6. So we have 12. Then copy 2x plus 1. Then 2 minus 1, or that's just 1. Then plus, here this is also a product rule, or you can expand it, or you multiply it, distribute it, but I just use product rule. So x minus 2, copy the first term, multiply it with the derivative of the second, then plus, copy the second term, 2x plus 1, multiply it with the derivative of the first. Then plus, again, this one we can use the product rule. It's actually the same as the first term. So we can just copy the first term. Here, I forgot to multiply this one with 2. Remember, 2, where does 2 came from? It's the derivative of 2x plus 1. That's the product rule. So here, I also do that. 12 times 2x plus 1 times 2. Or it's 24 times 2x plus 1. So this is a similar term here and here. So if we add them, we just multiply it by 2. So it will be 24 times 2. That will be 40. 40 times 2x plus 1. Plus, here we can distribute again the 24. So 2 times 24 is also 48. 48 times x minus 2. Then 24 times 2x plus 1. And this will be our y triple prime. You can expand or multiply the coefficient distributed inside the quantities. If you want, that's fine. But I'm lazy to do that. So let me just do this one. Then next, for the, actually we can simplify this one. We can more simplify. So that we can take the derivative of the next one faster. So here, this is the same term. We just expand it. So this will be 48 times 2. 2x plus 1. Then so 48 times 2, that's 96. No, this is 96x plus 48 times 1, so 48. Then plus 48x minus 48 times 2. It's 96 plus 24 times 2. It's 48x plus 24. Then we can add them. 96x plus 96, 48x plus 48x. So 96 times 2, and that will be 192x. Then for the constant, 48 minus 96 plus 24. So it will be equal to negative 24. And this will be the third order derivative. So it's better if you simplify this one. Then for the fourth order, y to the fourth. What's the derivative of 192x minus 24? What's the derivative of 192x? It's just 192. Minus the derivative of 24, that's equal to 0. So this is already our fourth order derivative. And for the fifth order derivative, it's the derivative of 192. Or the derivative of constant is 0. So that will be the fifth order. Okay, so that's higher order derivative. So you just take them step by step up to whatever you want to determine the order. So our next topic will be the implicit differentiation